Please subscribe to support the channel. What lies at the very edge of our solar system? It's a question that sparks curiosity in scientists, explorers, and anyone who has ever gazed at the night sky. At first, it seems like the answer should be simple. Surely the solar system ends where the last planet is, right? But the reality is far more fascinating, and far more complicated. Unlike the walls of a room or the clear shoreline of an ocean, the boundaries of the solar system are not sharply defined. Instead, they blur into layers upon layers of invisible forces, distant objects, and regions of space where the sun's influence gradually fades into the larger galaxy. In this sense, asking where does our solar system end isn't just about finding a line in the sand, it's about understanding what the solar system truly is and how far its presence stretches. This complexity is exactly what makes the question so intriguing. For centuries, people thought of the solar system as a collection of planets revolving around the sun, with Pluto marking the far edge. But as our knowledge expanded, we discovered that Pluto is only the beginning of a much larger frontier. We now know that the solar system extends vastly beyond the orbit of the last known planet, into territories populated by icy worlds, mysterious objects, and clouds of comets that may reach halfway to the next star. The deeper we explore, the more elusive the concept of an edge becomes. Is the end defined by the last physical object bound to the sun's gravity? Is it the place where the solar wind, the stream of charged particles from our star, finally weakens and gives way to the material of interstellar space? Or is it the invisible sphere where the sun's gravitational dominance gives way to the competing pull of neighboring stars? Each definition of the edge offers a different perspective, and each carries its own mysteries. This is why scientists approach the question carefully. It's not just about choosing one answer, it's about mapping out all the possible boundaries and understanding the roles they play in shaping our cosmic neighborhood. The edge of the solar system can be thought of as layered thresholds, like the outer rings of a growing tree, each one marking a new interaction between our sun and the galaxy beyond. So, when we ask where the solar system actually ends, we're really asking multiple questions at once. We're asking how far the sun's light, heat, and particles reach. We're asking how far its gravity stretches into space before giving way to the stars around us. We're asking where the known worlds end and where the uncharted regions begin. It's a question that challenges us to think bigger than just planets and moons. It challenges us to think of the solar system as a vast, dynamic, and evolving structure with boundaries that are as much about physics as they are about geography. In many ways, this search for the solar system's edge is also a reflection of our human desire to know where we belong. By finding where the solar system ends, we learn not only about the sun's domain, but also about its place within the Milky Way. It reminds us that while our solar system feels like home, it is just a tiny pocket within a galaxy of billions of stars, all surrounded by even larger mysteries. When we begin asking where the solar system ends, the next natural step is to first clarify what the solar system actually is. After all, if we don't define the system itself, how could we possibly know where its boundary lies? At first glance, the solar system seems easy to define. It's the sun and the collection of planets that orbit it. But just like with the question of the edge, things become far more complicated once we dig deeper. The solar system is not simply a family of planets circling their parent star. It is an intricate, interconnected structure that spans billions of kilometers, consisting of countless types of objects and invisible forces. At the heart of it all is, of course, the sun. This immense ball of nuclear fusion accounts for more than 99.8% of the entire solar system's mass. Every planet, every asteroid, every comet, every mote of dust is bound to the sun by its gravity. The sun is not just the center, it is the system itself. It provides the heat, the light, the energy, and the gravitational anchor that gives the solar system coherence. Around the sun orbit the 8 major planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, each with its own unique characteristics and system of moons. Earth's single moon seems modest compared to Jupiter's Galilean moons or Saturn's Titan and Enceladus, but together they represent another essential component of the solar system: natural satellites. Many of these moons are not merely passive bodies orbiting their planet. Some, like Europa and Enceladus, may harbor subsurface oceans, making them potentially more geologically active and biologically promising than even Mars. These moons show us that the solar system is not just about planets, It is a layered hierarchy of objects bound together through gravity. Then we have the smaller bodies. The asteroid belt between Mars and Jupiter holds millions of rocky fragments left over from the early formation of the solar system. These remnants are the building blocks that never coalesced into a planet, a living fossil record of the chaotic past of our cosmic neighborhood. Some asteroids are large enough to be considered dwarf planets, like Ceres, while others are no more than boulders adrift in space. Beyond Neptune lies another realm, the Kuiper Belt. This region contains icy worlds, dwarf planets like Pluto, Haumea, Makemake, and Eris, along with trillions of smaller frozen bodies. These objects are leftovers of the solar system's early days, frozen time capsules that have remained untouched for billions of years. They remind us that the solar system is not a tidy, planetary system ending at Neptune, but rather a sprawling expanse of matter that stretches outward in every direction. And yet, even the Kuiper Belt does not mark the true limit of the solar system. Farther still lies the scattered disk, with objects on highly elongated orbits, stretching them vast distances away from the Sun before gravity reels them back in. These populations of icy bodies remind us that the solar system extends not just in a flat disk, but in complex, three-dimensional structures reaching far into the deep. But defining the solar system cannot stop with physical objects. We must also consider the invisible but powerful domains carved out by the Sun's influence. One of the most important of these is the Sun's gravitational reach. Every body that orbits the Sun does so because of its pull. This gravitational influence extends billions of kilometers, and while it weakens with distance, it theoretically stretches until the point where the gravity of another star becomes stronger. This region is called the Sun's heliosphere, and it represents one potential definition of their edge. But gravity isn't the only force at play. The Sun also controls space through its energy output. The solar wind, a continuous flow of charged particles streaming outward from the Sun, creates a vast bubble around the solar system called the heliosphere. This bubble is filled with solar particles and magnetic fields, shielding us from much of the harsh radiation of the galaxy. The heliosphere extends far beyond the planets, enveloping the solar system in a protective cocoon. Its limits are another way of defining the system's edge, because outside of it, the galaxy begins to dominate. And there's yet another dimension to consider, the countless comets that occasionally blaze across our skies. Many of these comets originate from regions at the very edge of the solar system, particularly the Oort Cloud, a hypothesized spherical shell of icy objects perhaps stretching a light year away. Though we cannot see it directly, the comets it sends hurtling inward are powerful evidence that the solar system extends unimaginably farther than most of us ever consider. So when we talk about the solar system, we're not just talking about the Sun and the 8 planets. We're talking about a vast, layered domain, the Sun itself, the planets and their moons, the belts of asteroids and comets, the extended regions of icy debris, the invisible reaches of the Sun's gravity, and the heliosphere's protective bubble of plasma and magnetic fields. All of these together make up the true solar system. And this brings us full circle to our question of where it ends. Because if the solar system is not just planets, but a sprawling, multi-layered realm of physical bodies and invisible forces, then the edge becomes a question of which definition we use. Is it the edge of the heliosphere? The last dwarf planet orbiting in the scattered disk? The distant shells of the Oort Cloud? Or the outermost reach of the Sun's gravity, balancing against the pull of other stars? By defining the solar system in this way, we set the stage for exploring its many possible boundaries. And one of the most important of these invisible boundaries lies in the form of the heliosphere, the giant bubble carved by the Sun's wind as it pushes against the interstellar medium. To understand the edge, we must first understand this vast, dynamic bubble. Now that we've laid out what the solar system is and recognized that it's not simply a collection of planets but a vast, layered domain held together by the Sun's gravity and energy, we can dive deeper into one of its most fascinating features, the heliosphere. If the solar system is the Sun's kingdom, then the heliosphere is the great bubble-shaped shield it projects into the galaxy. It is invisible to the naked eye, yet it is one of the most consequential structures for life on Earth and for the very definition of where our solar system ends. The heliosphere is formed by the solar wind, a continuous stream of charged particles, mostly electrons and protons, that pour out from the outer layers of the Sun. Unlike the gentle breeze implied by its name, the solar wind races through space at supersonic speeds, sometimes reaching hundreds of kilometers per second. As this wind blows outward in every direction, it carries with it the sun's magnetic field, threading space with invisible lines of force. Together, these particles and fields carve out a bubble in the surrounding interstellar medium, the tenuous mix of gas, dust, and cosmic rays that fills the galaxy between stars. This bubble is the heliosphere. What's astonishing about the heliosphere is its sheer size. It dwarfs the orbits of the planets. Imagine Neptune, the farthest major planet, circling the Sun at about 30 astronomical units, AU. That's 30 times the distance from Earth to the Sun. The heliosphere stretches hundreds of AU farther than Neptune, wrapping all the planets in a protective cocoon. Its shape isn't perfectly spherical. Many scientists describe it as being somewhat comet-like, with a rounded nose facing the direction of the Sun's galactic motion and a long trailing tail stretching behind. In this sense, the solar system moves through the galaxy as though wrapped inside a gigantic bubble. The heliosphere serves as more than just an extension of the Sun's influence. It also acts as a shield. Beyond our solar system lies the constant bombardment of galactic cosmic rays, high-energy particles born from violent processes like supernova explosions. These rays can be harmful to both human health and spacecraft electronics. The heliosphere deflects and weakens a large portion of them, allowing Earth to remain relatively sheltered. Without this invisible bubble, life on our planet may have faced far harsher conditions, possibly even preventing complex organisms from flourishing. But the heliosphere is not static. It breathes and shifts with the Sun's activity. During periods of high solar activity, known as solar maximums, the solar wind intensifies, and the heliosphere may expand outward, pushing harder against the interstellar medium. During quieter times, called solar minimums, the bubble may shrink slightly, letting more cosmic rays seep into the solar system. This dynamic nature makes the heliosphere not just a boundary but a living extension of the Sun itself. Scientists have worked for decades to study this bubble, yet most of our information is indirect. We can't just take a picture of the heliosphere. It's too large, too diffuse, and too far away. Instead, we detect its existence through measurements of charged particles, cosmic ray counts, and magnetic fields. Still, we've made remarkable progress, particularly thanks to the Voyager spacecraft, which have traveled farther than any other human-made objects. They are the pioneers pushing against the bubble's edge, allowing us to measure where the heliosphere gives way to the galaxy beyond. One of the most intriguing aspects of the heliosphere is its role in defining the solar system's edge. For many scientists, the boundary of the heliosphere, the heliopause, is the most practical definition of where the solar system ends and interstellar space begins. This makes sense because beyond that point, the solar wind no longer dominates. Instead, the particles and fields of the galaxy itself take over. In this way, the heliosphere acts like a frontier outpost of the Sun's influence, a line drawn not by planets or comets but by plasma and magnetism. To appreciate the scale of this bubble, think of it this way. If the Sun were the size of a basketball, Earth would be a tiny grain of sand orbiting about 8 meters away. Neptune would orbit around 240 meters away. The heliopause, the outer edge of the heliosphere, would lie several kilometers farther out. That's how vast this structure is compared to the planets we typically focus on. It's a reminder that the solar system is much more than its familiar inner worlds. Understanding the heliosphere also has practical importance. As humanity dreams of interstellar travel, knowing where the heliosphere ends becomes crucial. The environment inside the bubble is dramatically different from the harsh conditions outside. Any spacecraft designed to leave the solar system must be prepared for the transition. Fewer protections from cosmic radiation, different magnetic conditions, and a new frontier of galactic particles streaming in. In a sense, the heliosphere is like Earth's atmosphere on a much grander scale. It separates inside from outside, and crossing it is a monumental step. By examining the heliosphere, we begin to see the solar system not as a neat set of orbits but as a dynamic bubble carved out in a galactic ocean. Its boundary is not defined by physical objects we can point to, but by interactions between the Sun's wind and the interstellar medium. It is here, at the limits of this bubble, where the solar wind first begins to falter. This transition marks the next great structure in our journey to the edge of the solar system. The termination shock, where the Sun's supersonic wind slows abruptly as it collides with the material of the galaxy beyond. Building on our understanding of the heliosphere, we now arrive at one of the most fascinating thresholds within this immense bubble, the termination shock. If the heliosphere is the great frontier carved by the sun's wind, then the termination shock is one of the first signs that this frontier is beginning to falter. It is the place where the solar wind, after racing outward for billions of kilometers, suddenly slows down, its supersonic momentum checked by the presence of the thin but powerful resistance of interstellar space. To truly grasp the significance of the termination shock, we need to picture the solar wind itself. For most of its journey outward from the sun, the wind travels faster than the speed of sound in the plasma environment. Supersonic in this context means moving so quickly that information about changes ahead of it cannot travel back upstream. The particles surge forward with tremendous energy, creating an expanding bubble of solar influence. But as they continue to push outward, they eventually encounter the interstellar medium, the sparse mixture of gas, dust, and magnetic fields that fills the space between stars. While the interstellar medium may seem almost empty, it exerts a subtle but persistent pressure. Imagine a speeding car hitting a patch of thick mud. No matter how fast it was going, resistance forces it to slow down dramatically. This is exactly what happens to the solar wind at the termination shock. It slams into the interstellar medium, loses its supersonic character, and drops to subsonic speeds. The change isn't just about speed, it also causes heating and compression of the plasma, creating a turbulent boundary zone. The termination shock is not a thin line but rather a broad region, and its distance from the sun is not constant. Scientists estimate that it lies somewhere between 75 to 90 astronomical units, AU, from the sun in the nose direction of the heliosphere, the side facing the sun's motion through the galaxy. To put that in perspective, Earth sits just $1 from the sun, while Neptune is about $30. So the termination shock is roughly 3 times farther out than Neptune, a vast gulf of emptiness before we even begin reaching the true edge of the heliosphere. Interestingly, the termination shock is not symmetrical. The solar system is not floating in a perfect void. It is moving through the galaxy at around 828,000 kilometers per hour, plowing into regions of varying density and magnetic conditions. This means the termination shock is closer in some directions and farther in others, depending on how strongly the interstellar medium pushes back. It's as if the sun's bubble is being squashed on one side and stretched on the other. The termination shock also marks an important scientific transition. Within this region, the solar wind begins mixing and interacting with galactic material, creating turbulence and complex plasma flows. For astrophysicists, studying this boundary provides a window into how our star interacts with the galaxy. It also offers clues about the protective power of the heliosphere, since cosmic rays from deep space are more likely to sneak past the heliosphere's defenses at its weaker, more turbulent borders. For decades, the termination shock was purely theoretical. Astronomers predicted its existence based on models of solar wind behavior, but it remained unseen. That changed thanks to the Voyager missions. In 2004, Voyager 1 crossed the termination shock at about $94, becoming the first spacecraft to experience this strange region. The data it sent back revealed a sharp slowdown of the solar wind, a rise in energetic particles, and chaotic changes in magnetic fields, clear evidence that it had passed through the termination shock. Voyager 2 followed a few years later, in 2007, crossing the shock at about $84. The difference in distances highlighted just how irregular and asymmetrical this boundary really is. These discoveries transformed the termination shock from theory into reality. For the first time, humanity had direct evidence of where the solar wind begins to fail. It was a stunning confirmation that the sun's bubble does not stretch infinitely but instead is shaped and sculpted by the galaxy around it. The termination shock is also deeply symbolic. It represents a zone where the familiar influence of our star starts giving way to the unknown. Inside the termination shock, space is still largely the sun's domain. Its winds dominate, its fields dictate the environment. But beyond it lies a new realm, a place where galactic forces begin pressing inward. It is the first step on a journey from a solar system-centered universe into a galactic one. Beyond the termination shock lies yet another critical layer, the heliosheath. This is the vast, turbulent region where the solar wind, slowed and battered, struggles against the interstellar medium. It's a cosmic battleground where pressure, magnetism, and plasma flows collide in unpredictable ways. Understanding this region takes us one step closer to the ultimate boundary, the heliopause, where the sun's influence finally ends. Coming out of the termination shock, the solar wind no longer races outward supersonically. It has been slowed, compressed, and heated, marking the beginning of one of the most fascinating and chaotic regions of the solar system's frontier, the heliosheath. If we think of the heliosphere as a vast bubble inflated by the sun's wind, then the heliosheath is the thick outer skin of that bubble. It is the turbulent transition zone where the weakened solar wind and the incoming pressure of the interstellar medium clash in a cosmic tug-of-war. Inside the heliosheath, the solar wind has lost much of its momentum, but it still flows outward, dragging the sun's magnetic field with it. At the same time, the interstellar medium, the thin but constant presence of gas, dust, and magnetic fields beyond our solar system, pushes back. Neither side wins outright. Instead, they grind against one another, producing a region of turbulence, eddies, and compressed plasma. It is not a peaceful boundary, but rather a stormy frontier, shaped by the dynamic interplay of two massive forces. This turbulence makes the heliosheath an incredibly complex environment. The slowed solar wind piles up, creating higher densities of particles compared to the more empty regions inside the heliosphere. Magnetic fields twist and fold, sometimes reconnecting in bursts of energy. Energetic particles, trapped between the outward push of the solar wind and the inward squeeze of the galaxy, bounce back and forth, creating radiation levels that fluctuate wildly. It is in many ways the no-man's land of the solar system, where the rules we are used to inside the sun's domain begin to break down. The size of the heliosheath is enormous. It spans tens of astronomical units in thickness, so vast that a spacecraft traveling at tens of thousands of kilometers per hour can take years to cross it. Voyager 1 entered the heliosheath after passing through the termination shock in 2004 and did not exit until 2012, when it finally reached the heliopause. That means it spent about 8 years traveling through this turbulent region. Voyager 2 had a similar journey, entering the heliosheath in 2007 and crossing into interstellar space in 2018. These long transits reveal just how massive and complex the heliosheath really is. What's even more fascinating is that the heliosheath isn't the same in all directions. Because the sun is moving through the galaxy, the heliosphere as a whole is shaped somewhat like a comet, with a blunt nose facing the sun's direction of motion and a long tail streaming behind it. As a result, the heliosheath is thicker in some places and thinner in others, reflecting the pressure balance between the solar wind and the interstellar medium. Voyager 1 and Voyager 2 crossed the heliopause at different distances from the sun, about $121 and $119 respectively, demonstrating this asymmetry. From a scientific perspective, the heliosheath is one of the most important laboratories for studying plasma physics and cosmic rays. It is here that galactic cosmic rays, high-energy particles from distant supernovae and other violent astrophysical events, begin to leak into the solar system in significant numbers. By monitoring how these cosmic rays change inside the heliosheath, scientists gain insights into how well the heliosphere shields us from interstellar radiation. Voyager's instruments provided a treasure trove of data, showing that cosmic ray intensity began to climb steadily as the spacecraft moved through the heliosheath, signaling that they were nearing the very edge of the sun's protection. The heliosheath also helps us understand how stellar winds shape the environments around other stars. Every star with a stellar wind creates a bubble similar to our heliosphere, and by studying ours, we can extrapolate to others. This is crucial for exoplanet science. If a planet orbits within a strong stellar bubble, it may be shielded from harsh galactic radiation, making it more hospitable for life. In this way, our study of the heliosheath doesn't just tell us about our own solar system, it informs our search for habitable worlds beyond. Yet for all we've learned, the heliosheath remains mysterious. Voyager's data gave us a first glimpse, but the instruments were limited and not designed for this environment. They couldn't capture everything. New missions are being planned to study this region more comprehensively, to measure the flows of particles, to map the shape of the bubble more accurately, and to determine how the heliosphere's shield really works. The heliosheath, then, is not merely a transition zone. It is a cosmic battlefield where the solar wind meets the galaxy head-on. It is the place where the sun's influence falters but does not yet end, a stormy region that prepares us for the final and most profound boundary of all, the heliopause. The heliopause is the point where the balance tips completely, where the solar wind's outward push is finally stopped by the galaxy's inward squeeze, and interstellar space truly begins. As we emerge from the chaotic turbulence of the heliosheath, we approach one of the most significant boundaries in all of space science, the heliopause. If the termination shock was the slowing of the solar wind and the heliosheath was the battleground of pressures, then the heliopause is the final frontier, the line in the cosmic sand where the sun's outward breath is halted completely by the galaxy beyond. For many astronomers and astrophysicists, this is the most practical, physical definition of where the solar system ends and true interstellar space begins. The heliopause is not a material wall or a barrier that one could see or touch. It is, instead, a boundary defined by balance. On one side lies the solar wind, weakened and stretched thin after its long journey outward. On the other side lies the interstellar medium, the ancient mixture of hydrogen, helium, dust, and magnetic fields that pervades our galaxy. At the heliopause, these two opposing forces reach equilibrium. The solar wind can push no farther, and the interstellar medium cannot push inward beyond this point. It is here that the solar bubble ends and the galactic ocean begins. What makes the heliopause so intriguing is its role as both an ending and a beginning. Inside it, everything is touched by the sun, its particles, its magnetic fields, its protective shield. Outside it, everything belongs to the galaxy. Foreign particles, alien magnetic orientations, and cosmic rays traveling unimpeded from distant explosions. Crossing the heliopause means leaving behind the solar system's domain and stepping into a universe shaped by events far beyond our star. Voyager 1 gave us humanity's first direct evidence of this boundary. After crossing the termination shock in 2004 and spending years traversing the heliosheath, the spacecraft detected a sudden and dramatic shift in 2012, at about 121 astronomical units from the Sun. The density of charged particles around it changed. The intensity of cosmic rays spiked. Most tellingly, the magnetic field's orientation shifted from being aligned with the Sun's influence to that of the interstellar medium. These were the unmistakable signs that Voyager 1 had crossed the heliopause and entered interstellar space. Voyager 2 confirmed this crossing in 2018, at a slightly closer distance of about 119 Australian dollars, showing once again that the heliopause is not a perfect sphere but a rippling, irregular boundary influenced by both solar activity and galactic conditions. For scientists, this moment was nothing short of historic. Humanity had finally, for the first time, touched interstellar space, not in theory or in models, but with real instruments, real data, and a real machine carrying our presence into the galaxy. It was the cosmic equivalent of a sailor passing beyond the sight of land for the very first time, into a vast and uncharted ocean. The heliopause is also deeply important for understanding our own survival. Inside the heliosphere, the sun's bubble deflects and filters cosmic rays, reducing their intensity. Outside, those rays are far more numerous and dangerous. Without the heliosphere's shield, Earth and its life forms would be exposed to levels of radiation that could alter DNA, disrupt ecosystems, and damage the atmosphere. In this sense, the heliopause is not just a boundary of interest to science, it is part of the protective envelope that makes life on Earth possible. The shape and behavior of the heliopause are still mysteries. Does it have a long trailing tail like a comet, streaming behind the sun as it moves through the galaxy? Or is it more compact, shaped by pressure and magnetic reconnect ion in ways we don't yet fully understand? Voyager's limited instruments could not map it completely, and no other spacecraft has yet traveled that far. But new missions are being planned that may one day chart its contours, giving us a clearer picture of this cosmic boundary. The heliopause also forces us to rethink what it means to say we've left the solar system. Some argue that as long as a spacecraft is still gravitationally bound to the Sun, which can extend nearly a light-year outward, it is technically still within the solar system. Others argue that the heliopause, as the practical limit of the Sun's energetic influence, is the truest definition of the edge. This duality shows that the solar system doesn't have a single, sharp ending, but rather a series of overlapping boundaries, each meaningful in its own way. And yet, for all these debates, the heliopause retains a poetic resonance. It is the end of the sun's breath. It is the outer wall of our cosmic home. To cross it is to step into the galaxy, to touch the medium between stars, and to glimpse a reality that extends unimaginably farther than our solar system's modest bubble. For humanity, standing on this threshold through our robotic explorers is both humbling and inspiring. But our journey doesn't stop at the heliopause. Beyond this frontier, the Voyagers have entered interstellar space, carrying with them not only scientific instruments but also the golden records, time capsules of Earth's music, languages, and images meant for any intelligence that might someday encounter them. Their passage reminds us that while the heliopause may be the boundary of the Sun's influence, it is also the doorway to something larger, the galaxy itself. The story of the heliopause, however, cannot be told without mentioning the very missions that gave us this knowledge, the Voyagers. Their odyssey is one of the most remarkable achievements of human exploration, and their crossing of this boundary is one of the most significant milestones in our quest to understand where the solar system truly ends. When we speak of the heliopause as the place where the Sun's influence finally yields to the galaxy beyond, we cannot ignore the extraordinary machines that made this more than an idea, Voyager 1 and Voyager 2. Without these twin spacecraft, the heliopause would remain a boundary defined only by theory and models, elusive and uncertain. Thanks to them, we have touched this frontier with real instruments and transformed speculation into discovery. Their story is not only one of scientific triumph but also of human imagination and persistence, an odyssey that continues to unfold nearly half a century after their launch. The Voyager program began in the late 1970s, during an extraordinary alignment of the outer planets that occurs only once every 176 years. NASA seized this rare opportunity to send spacecraft on what became known as the Grand Tour, a trajectory that would allow them to visit Jupiter, Saturn, Uranus, and Neptune with carefully timed gravitational assists. Voyager 2 launched first, on August 20, 1977, followed by Voyager 1 on September 5 of the same year. Though they carried similar instruments and shared the same mission design, their paths diverged. Voyager 1 took a faster route toward Jupiter and Saturn, while Voyager 2 would become the only spacecraft in history to fly by all four giant planets. During their planetary encounters, the Voyagers revolutionized our understanding of the outer solar system. They revealed active volcanoes on Jupiter's moon Io, geysers on Neptune's moon Triton, intricate details of Saturn's rings, and the strange atmospheres of Uranus and Neptune. Each discovery reshaped textbooks and opened new questions, laying the foundation for all planetary science missions that followed. But what made the Voyagers truly historic was not just their planetary tour, it was their trajectory toward the outer edge of the solar system and beyond. After completing their planetary encounters, both Voyagers continued on escape trajectories from the Sun. They were never intended to stop at Neptune or Saturn. They were built with the foresight to keep going indefinitely, powered by nuclear generators that could provide electricity for decades. In doing so, they became the first emissaries of humanity to reach the solar system's edge. Voyager 1 reached the termination shock in December 2004, at about 94 astronomical units (AU) from the Sun. At that distance, signals from the spacecraft took nearly 14 hours to reach Earth. The data it sent back confirmed the dramatic slowing of the solar wind and the beginning of the turbulent heliosheath. Voyager 2 crossed the termination shock in 2007 at a closer distance of about $84, confirming that the boundary is not uniform but shaped by the pressure of the interstellar medium. 4 years, both spacecraft traveled through the heliosheath, sending back invaluable data about this turbulent outer region. Then, in August 2012, Voyager 1 made history. It crossed the heliopause at a distance of about $121 from the Sun, becoming the first human-made object to enter interstellar space. The signs were unmistakable. Instruments detected a sudden spike in cosmic rays from outside the solar system, while the flow of solar particles dropped to nearly nothing. The magnetic field orientation shifted, showing that Voyager had left the Sun's bubble and entered the galactic medium. Humanity had finally crossed into the space between stars. Voyager 2 followed 6 years later, crossing the heliopause in November 2018 at a distance of about $119. Its instruments, still in better condition than those on Voyager 1, provided even more detailed measurements. It confirmed that the heliopause is indeed a sharp boundary, though slightly rippled and uneven, and it reinforced the reality that this frontier is not fixed but dynamic, shifting with changes in solar activity and interstellar pressure. The importance of these crossings cannot be overstated. For the first time in history, we had direct, physical measurements of the boundary between the solar system and interstellar space. Before the Voyagers, the heliopause was a theoretical construct, Afterward, it became a tangible reality, mapped by human-made explorers carrying instruments designed decades earlier. This achievement is comparable to the first circumnavigation of Earth or the first steps on the Moon. It is humanity extending its reach beyond the familiar into the truly unknown. What makes the Voyager missions even more remarkable is their endurance. Launched in the era of rotary phones and mainframe computers, they were not designed with today's technology. Their memory is measured in kilobytes, their transmitters are weak, and their power sources slowly decay with time. Yet, through careful planning, brilliant engineering, and dedicated mission teams, they continue to function, sending back faint signals that must be captured by NASA's deep space network of massive radio antennas. Each byte of data is precious, carrying the whispers of a spacecraft traveling more than 20 billion kilometers away. Beyond their scientific instruments, the Voyagers also carry something profoundly symbolic: the Golden Record. This phonograph record, designed by Carl Sagan and a team of visionaries, contains music, greetings, and images from Earth, a time capsule of humanity meant for any extraterrestrial intelligence that might one day encounter these spacecraft. The Golden Record transforms the Voyagers from mere scientific probes into ambassadors of our species, carrying a message of who we are to the galaxy. In this sense, their crossing of the heliopause was not only a scientific milestone but also a poetic one, the first human-made objects to carry our story into interstellar space. Today, the Voyagers continue their journey outward, traveling at tens of thousands of kilometers per hour. They will remain within the Sun's gravitational influence for many thousands of years, but they will never return. Long after their power runs out and their instruments fall silent, they will drift silently among the stars, the most distant relics of human civilization. Their odyssey shows us what is possible when curiosity and ingenuity drive exploration. They reveal to us that the heliopause is real, that interstellar space is within reach, and that the edge of the solar system is not the end of exploration but the beginning of a much larger journey. And while the Voyagers confirmed the heliopause as a boundary, they also opened new questions. What lies beyond, in the interstellar medium? How does cosmic radiation behave there? What mysteries await in the galactic ocean we've only just begun to touch? To answer these questions, we turn to the evidence that made Voyager's crossing clear in the first place: the changes in cosmic rays. These high-energy particles, born in the hearts of exploding stars, served as markers of the boundary and a reminder of the immense power of the galaxy beyond our bubble. As Voyager 1 and Voyager 2 pushed through the heliosheath and finally into interstellar space, one of the most decisive pieces of evidence that they had crossed the heliopause came not from pictures or dramatic visual cues, because out there are no landmarks, but from the invisible rain of high-energy particles called cosmic rays. These particles, traveling at nearly the speed of light, became the breadcrumbs that revealed humanity's first steps outside the Sun's protective bubble. Cosmic rays are born in the most violent events in the universe: exploding stars, colliding neutron stars, and perhaps even black hole jets. They are mostly protons, with some electrons and heavier atomic nuclei mixed in. Unlike the charged particles of the solar wind, which are relatively low energy, cosmic rays are extraordinarily energetic. Some are so powerful that even the most advanced particle accelerators on Earth cannot come close to replicating their energies. Inside the heliosphere, the solar wind and the Sun's magnetic field act as a shield, deflecting and scattering many of these galactic cosmic rays. The stronger the solar activity, the more inflated the heliosphere becomes, and the more effectively it blocks cosmic rays from entering. This protective shield is not perfect. Cosmic rays still reach Earth, and they are one reason astronauts face radiation risks in space, but it reduces their intensity significantly. Without the heliosphere, Earth would be bombarded by far higher levels of radiation, and life might not have had the stable conditions needed to thrive. So, when Voyager 1 approached the edge of the heliosphere, scientists knew that one telltale sign of crossing into interstellar space would be a sudden increase in cosmic ray counts. Inside the heliosphere, cosmic rays are partially deflected. Outside, in the galactic medium, they are everywhere, pouring in from all directions. Sure enough, in August 2012, Voyager 1's detectors recorded a sharp and sustained spike in galactic cosmic rays, while at the same time, the presence of solar origin particles plummeted. This dramatic shift told scientists that the spacecraft had passed through the Sun's bubble and entered the broader galactic environment. Voyager 2 confirmed this picture 6 years later, in November 2018. Its instruments showed the same unmistakable trend, a steep drop in solar particles and a strong rise in cosmic rays from outside. What made Voyager 2's crossing particularly valuable was that some of its detectors were still fully functional, giving researchers a clearer, more detailed measurement than Voyager 1 could provide. Together, the two spacecraft painted a compelling portrait of what happens at the heliopause, a sudden handoff between solar influence and galactic forces, with cosmic rays serving as the signature of that passage. But cosmic rays are not just useful as markers of the heliopause. They also carry deep scientific importance. By studying their intensity, direction, and energy levels, scientists gain insights into the structure of the heliosphere and its effectiveness as a shield. For example, during solar maximum, when the Sun is most active, the heliosphere expands and deflects more cosmic rays, leading to lower counts inside. During solar minimum, when the Sun is quiet, the heliosphere contracts, and cosmic ray levels inside increase. Voyager's data confirmed this dynamic, but at the outermost edge of the heliosphere, where the shielding is weakest, the changes were far more dramatic. Even beyond the heliopause, the story of cosmic rays is rich. Voyager's instruments showed that the interstellar medium is filled with these high-energy particles, but they are not uniformly distributed. Instead, their patterns are shaped by magnetic fields, shock waves, and perhaps even distant stellar explosions. By continuing to measure them, Voyager is helping map the invisible architecture of the galaxy itself. Each cosmic ray detected is a messenger from some distant, violent event, carrying information about processes far beyond our solar system. The implications extend to humanity's future in space. If we dream of sending crewed missions beyond the heliosphere, or even interstellar probes carrying life, cosmic rays will be one of the greatest hazards. They can penetrate spacecraft hulls, damage electronics, and harm biological tissue. Learning how they behave at the solar system's edge is critical for designing the protective technologies that future explorers will need. Voyager's data is laying the groundwork for this knowledge, decades in advance of when it may become crucial. In this way, cosmic rays are both a challenge and a gift. They mark the boundary of the Sun's protective bubble, revealing where the solar system ends in a practical sense, but they also connect us to the wider galaxy, serving as natural messengers from faraway stars and cataclysms. Voyager's ability to detect their rise was like a traveler finally feeling the spray of ocean waves after leaving the shelter of a harbor. It was the unmistakable sign that the ship had reached open waters. Yet it is important to remember, the heliopause and the rise in cosmic rays do not mean the solar system ends neatly at Pluto, as many once thought. The true edge lies much farther out, in places populated not by planets but by icy worlds, belts of debris, and distant objects that orbit our Sun across unimaginable distances. To fully appreciate just how far the solar system stretches, we must look beyond the familiar planetary orbits to the realms of Pluto, the Kuiper Belt, and the strange, icy frontiers that lie beyond. When most people picture the edge of the solar system, they often think of Pluto. For much of the 20th century, Pluto was hailed as the ninth and most distant planet, the lonely guardian of the outer frontier. Textbooks and diagrams often portrayed it as the final outpost, orbiting the Sun at a chilly, remote distance of about 40 astronomical units, AU. To school children and the general public alike, Pluto was the edge of everything. But as science advanced, this view turned out to be a simplification, one that underestimates the sheer scale and complexity of our solar system. Pluto is, without question, fascinating. Discovered in 1930 by Clyde Tombaugh, it was long celebrated as the little planet on the outskirts, a cosmic underdog orbiting in the shadow of the giants. Its eccentric, tilted orbit sets it apart from the other planets, sometimes bringing it closer to the Sun than Neptune. For decades, Pluto seemed unique, the lone icy sentinel marking the end of the Sun's planetary family. But then discoveries began to challenge this narrative. In 1992, astronomers found the first Kuiper Belt object, another icy world orbiting beyond Neptune. Soon after, dozens, then hundreds, and eventually thousands of such objects were discovered. Pluto was no longer unique but one of many icy bodies in this vast region. This realization ultimately led to Pluto's reclassification in 2006 as a dwarf planet, grouped with other large Kuiper Belt objects such as Eris, Haumea, and Makemake. What had once been the end of the solar system was revealed to be just the beginning of an entire new frontier. The Kuiper Belt stretches from about $30 Australian near Neptune's orbit, to around $50 from the Sun. It is filled with icy planetesimals, frozen relics from the early solar system that never coalesced into a planet. These objects are time capsules, preserving the chemistry and conditions of the solar system's infancy. Pluto, rather than being the final chapter, is simply the largest character in a vast cast. Beyond Pluto lie countless more bodies, some nearly as large, orbiting in strange resonances and elongated paths. But even the Kuiper Belt is not the edge. It's more like a thick ring around the Sun, a belt of debris orbiting in relatively organized patterns. Beyond it lies the scattered disk, a region populated by icy bodies on much more eccentric and tilted orbits, some reaching hundreds of AU from the Sun. Objects in this region, like the dwarf planet Eris, travel on elongated paths that take them far out into the solar system's hinterlands before returning closer in. This scattered disk pushes the solar system's physical presence much farther than Pluto, showing us that the Sun's family stretches outward like ripples from a stone dropped in water. And beyond even the scattered disk lie extreme trans-Neptunian objects, like Sedna. Sedna has an orbit so elongated that it swings out to nearly $1,000 from the Sun, 25 times farther than Pluto at its average distance. Sedna spends most of its 11,400-year orbit in darkness, far removed from the planetary region. Its existence suggests the influence of forces we don't yet fully understand, possibly even the gravitational tug of a hidden planet, what some call Planet 9. Sedna and its kin remind us that the solar system is not neatly confined to the orbits of the known planets but is an extended, evolving structure that defies simple boundaries. In this sense, the discovery of Pluto was not the discovery of an edge, it was the discovery of a doorway. Pluto and the Kuiper Belt mark a transition between the orderly architecture of the 8 major planets and the chaotic, distant frontier of icy debris, dwarf planets, and possible unseen worlds. Far from being the end of the solar system, Pluto is simply one milestone along a journey that extends thousands of times farther outward. This perspective fundamentally reshapes how we think about the solar system. Instead of imagining it as a neat collection of planets ending with Pluto, we now understand it as a layered structure, stretching outward in belts, disks, and clouds of objects that gradually thin into the interstellar medium. The true edge is not just a planet, or even a belt, but a distant and diffuse boundary where the Sun's gravitational grip finally fades into the galaxy. Pluto, however, retains its symbolic place in our imagination. The New Horizons mission, which flew past Pluto in 2015, revealed a world more complex and alive than anyone expected, with mountains of water ice, nitrogen glacier, and a thin atmosphere. It reminded us that even at the solar system's perceived edge, there is wonder, activity, and mystery. But New Horizons did not stop at Pluto. It continued into the Kuiper Belt, where it visited the object Arakoth in 2019, proving that the story of Pluto and beyond is ongoing. So when we ask where the solar system ends, Pluto should not be thought of as the final frontier but as a gateway. It is the threshold to the Kuiper Belt, the scattered disk, and ultimately the Oort Cloud, a vast, spherical shell of icy objects that may extend nearly a light-year away. The solar system does not end with a single dwarf planet. It sprawls outward into realms we have only just begun to explore. And the next step beyond Pluto's symbolic edge is the Kuiper Belt itself, a sprawling, icy domain filled with dwarf planets and countless smaller objects. To understand the solar system structure, we must journey deeper into this frozen wilderness, where worlds like Eris, Haumea, and Makemake orbit silently in the cold. Beyond Pluto, the solar system opens into a frozen, mysterious region known as the Kuiper Belt. This is a realm that fundamentally reshaped our understanding of the Sun's reach. While the planets dominate the inner solar system, the Kuiper Belt sprawls in the outer regions, beyond Neptune, as a vast repository of icy bodies, dwarf planets, and primordial remnants from the birth of the Sun. It is a region that is at once distant, cold, and incredibly rich in clues about the early solar system. The Kuiper Belt extends roughly from 30 to 50 astronomical units, AU, from the Sun. For perspective, Earth sits at $1, Neptune at $30, and Pluto, once thought to be the edge, at about $39. Beyond these orbits, the Kuiper Belt begins, a dense disk of icy objects left over from the solar system's formation. These are not just random debris. Many are considered planetesimals, the building blocks that, in some regions closer to the Sun, came together to form planets. Out here, however, The gravity of Neptune and the Sun's weaker influence prevented these icy bodies from coalescing fully, leaving a frozen landscape populated by hundreds of thousands, possibly millions, of objects. Among the most prominent Kuiper Belt objects are dwarf planets like Eris, Haumea, and Makemake. Eris, discovered in 2005, is slightly smaller than Pluto but more massive, and its discovery played a major role in Pluto's reclassification. Haumea is known for its rapid rotation and elongated, egg-shaped appearance, making it unlike any other body in the solar system. It also has a family of smaller fragments orbiting nearby, suggesting a past collisional event. Makemake, discovered in 2005, is another large, bright Kuiper Belt object with a slow, more regular rotation and a thin atmosphere. These dwarf planets highlight the diversity of the Kuiper Belt. Each is unique, yet all share the common heritage of icy formation and distant orbits. The Kuiper Belt is far more than a collection of dwarf planets. It contains countless smaller icy bodies, ranging from kilometers to hundreds of kilometers across, many with elongated, tilted, or eccentric orbits. Some are locked in resonances with Neptune, gravitationally influenced so that their orbits are stable over billions of years. Others are scattered more chaotically, forming the transition zone toward the even more distant scattered disk. These objects are often red or neutral in color, a result of surface ices being irradiated by the sun and cosmic rays over billions of years. Their compositions, water ice, methane, ammonia, and nitrogen ices, provide a direct window into the materials present during the solar system's formation. One of the most fascinating aspects of the Kuiper Belt is its dynamic interactions with the planets. Neptune, the outermost giant, shepherds many Kuiper Belt objects through gravitational resonances, effectively stabilizing their orbits over long periods. Yet these interactions can also send some objects on chaotic paths, ejecting them into the scattered disk or even sending them inward toward the inner solar system as short-period comets. This constant gravitational push and pull illustrates that the Kuiper Belt is not a static region. It is alive with motion, a dynamic periphery of the Sun's influence. The discovery and study of the Kuiper Belt has also reshaped our view of planetary formation. For centuries, astronomers imagined the solar system as a neatly arranged set of planets orbiting the Sun. But the Kuiper Belt revealed a much more complex, layered structure, populated by a vast number of icy remnants. These remnants are fossils from the early solar system, preserved in the extreme cold of the outer reaches. Unlike the inner planets, which have undergone geological evolution, erosion, and volcanic activity, the Kuiper Belt's objects have remained largely untouched, providing an almost pristine record of the materials from which the planets were built. NASA's New Horizons mission brought the Kuiper Belt into vivid detail. After its historic flyby of Pluto in 2015, the spacecraft continued deeper into the Kuiper Belt, passing by the object Arrokoth in 2019. Arrokoth, formerly nicknamed Ultima Thule, revealed a contact binary structure, two lobes gently fused together, offering unprecedented insights into how planetesimals may have formed in the early solar system. This flyby confirmed that the Kuiper Belt is not just a collection of distant rocks, but a laboratory for understanding the processes that built the planets themselves. The Kuiper Belt also bridges the gap to more distant, less understood regions. Beyond its outer edge, at $50 and beyond, lies the scattered disk, where objects are more eccentric, inclined, and influenced by distant gravitational interactions. The Kuiper Belt, in this sense, is the structured beginning of a vast, icy frontier, while the scattered disk and eventual Oort Cloud extend that frontier into realms that are even more alien and distant. Importantly, the Kuiper Belt reshapes our perception of the solar system's scale. Pluto was once seen as the edge, Neptune as the last world of significance. But with the Kuiper Belt, we now understand that the Sun's family extends much farther, populated by numerous icy worlds and dwarf planets that challenge traditional definitions. This is a solar system of layers, with each successive ring of objects, planets, Kuiper Belt, scattered disk, and ultimately the Oort Cloud, expanding the boundary and complexity of our stellar neighborhood. The Kuiper Belt, therefore, is not merely a collection of distant, frozen bodies. It is a critical transitional region, connecting the familiar planets to the deeper, more remote parts of the solar system. It is a region where the past of the solar system is frozen in ice, yet where dynamic forces, gravity, collisions, and resonances, still actively shape its evolution. As we continue outward, beyond the Kuiper Belt lies the scattered disk, an even more chaotic and distant realm of icy objects. It is here that the solar system stretches toward the limits of the Sun's gravitational reach, teasing the boundary between the Sun's influence and the interstellar medium. Beyond the structured expanse of the Kuiper Belt lies a more chaotic, enigmatic, and sparsely populated region known as the scattered disk. While the Kuiper Belt can be thought of as the orderly outer ring of the solar system, where objects follow relatively stable orbits influenced by Neptune, the scattered disk is a realm of extreme eccentricity and gravitational unpredictability. It represents a transitional zone between the Kuiper Belt and the outermost boundaries of the solar system, a place where the Sun's gravity still dominates but the influence of distant forces begins to grow. The scattered disk begins roughly around 50 astronomical units, AU, from the Sun but extends hundreds of AU outward, far beyond the orbit of Pluto. Its members are primarily icy bodies, composed of frozen water, methane, ammonia, and other volatiles, remnants of the early solar system. Unlike the more circular orbits of the Kuiper Belt objects, scattered disk objects, SDOs, have highly elongated and inclined orbits. This means that they can travel extraordinarily far from the Sun at the aphelion of their orbit, only to return much closer at perihelion, creating trajectories that span vast distances across the solar system. One of the most famous scattered disk objects is Eris, which rivals Pluto in size and mass and helped prompt Pluto's reclassification as a dwarf planet. Eris has an extremely elongated orbit that takes it roughly $38 from the Sun at its closest approach and nearly $98 at its farthest point. Its orbit, like many SDOs, is heavily influenced by Neptune's gravity. These gravitational interactions are not stable over billions of years. Objects in the scattered disk may have been perturbed from the Kuiper Belt by Neptune or even by passing stars during the Sun's early history in a stellar cluster. In this sense, the scattered disk is a dynamically excited region, a kind of outer solar system wilderness, where the rules are less predictable than in the inner planetary system. The scattered disk also contains a number of smaller, less massive objects that are difficult to detect but significant in terms of population. Their elongated orbits make them less likely to be found near the Sun, so surveys only catch a fraction of the total population. These objects provide important clues about the gravitational history of the outer solar system. For example, their current distribution suggests that Neptune migrated outward early in the solar system's history, scattering icy bodies into the disk in a chaotic process that left behind both stable and unstable orbits. Studying these objects allows scientists to reconstruct the solar system's formation and the early movements of the giant planets. Another defining characteristic of the scattered disk is the presence of extreme trans-Neptunian objects, ETNOs, which follow even more eccentric orbits. These objects, such as Sedna and 2012 VP-113, have perihelia far beyond Neptune, meaning they never come close enough to be influenced by the giant planets in a conventional way. Their orbits suggest that forces beyond the known planets may have played a role, possibly hinting at unseen massive objects, such as the hypothesized Planet 9, or the influence of passing stars early in the solar system's history. The scattered disk, therefore, represents both a known chaotic frontier and a potential doorway to discovering hidden components of the solar system. The scattered disk structure also helps bridge our understanding of other solar system features. It gradually transitions into the inner Oort Cloud, where icy bodies orbit at distances thousands of AU from the Sun. While the scattered disk remains bound tightly enough to the Sun that it is still considered part of the solar system proper, it is the staging ground for objects that may eventually be ejected into interstellar space or perturbed inward as long-period comets. In this sense, it plays a critical role in the movement of material throughout the solar system and into the broader galaxy. Observationally, the scattered disk is challenging to study because its members are faint, distant, and widely separated. However, advances in telescopes, such as the Subaru telescope and the Hubble Space Telescope, have revealed many SDOs, helping to map their distribution and characteristics. These observations show a population dominated by small, icy bodies, many with unusual colors and surface properties, reflecting a mix of primordial material and radiation-altered ices. Each discovery adds another piece to the puzzle of how the outer solar system evolved and how the Sun's gravitational influence extends far beyond the known planets. The scattered disk also highlights the immense scale of the solar system. While Pluto orbits at roughly $39 and the Kuiper Belt ends near $50, the scattered disk extends hundreds of AU outward, gradually fading into the outer reaches where the Sun's gravitational influence weakens. Its existence challenges our intuition. The solar system is not a neat set of planetary orbits, but a vast, multi-layered structure with overlapping regions of stability, chaos, and transition. It's a reminder that the edge is not simply a line but a gradient, stretching farther than the eye can see and beyond any planet's orbit. Ultimately, the scattered disk prepares us for the even more mysterious and distant populations of the solar system, the inner and outer Oort Cloud. These regions, only theorized but critical for understanding long-period comets and the Sun's ultimate gravitational domain, represent the final frontier of the solar system's material presence. Before we reach that boundary, however, there are unusual, extreme objects like Sedna that hint at gravitational influences far beyond even the scattered disk. Beyond the scattered disk lies a realm that is even more distant, more mysterious, and more sparsely populated: the world of extreme trans-Neptunian objects, or ETOs. Among the most famous of these is Sedna, discovered in 2003, whose orbit takes it on a slow, lonely journey around the Sun every 11,400 years. These oddball objects, including Sedna, 2012 VP-113, and a handful of others, occupy orbits so elongated and detached from the giant planets that they cannot be explained solely by the gravitational influence of Neptune or the known solar system architecture. Their existence challenges our understanding of the outer solar system and hints at forces and regions far beyond the scattered disk. Sedna is particularly striking. Its perihelion, the closest point to the Sun in its orbit, is about 76 Australian dollars, nearly twice the distance of Pluto. Its aphelion, however, is estimated to reach around 937 Australian dollars, pushing it into the distant outskirts of the solar system where the Sun's influence is incredibly weak. For most of its orbit, Sedna is in near-total darkness, surrounded by frigid temperatures and cosmic radiation. This extreme orbit is highly unusual and cannot be accounted for by interactions with Neptune alone. It suggests the presence of a gravitational influence that operates over vast distances, perhaps an undiscovered massive object, a passing star from the Sun's early history, or even tidal forces from the galactic disk itself. Sedna and similar objects are often described as detached because their orbits do not intersect with the scattered disk or other known populations in a predictable way. They serve as natural markers of the solar system's farthest reaches, revealing the gravitational footprint of the Sun at distances nearly an order of magnitude greater than the Kuiper Belt. Studying their orbits allows scientists to model the distribution of mass and potential unseen influences in the outer solar system. 2012 VP-113, nicknamed Biden in its informal designation, is another ETNO with a perihelion well beyond 80 Australian dollars. Like Sedna, it travels in a highly elliptical orbit and is mostly isolated from the perturbations of the giant planets. Its discovery reinforced the idea that there may be a whole population of such distant objects, hinting at unseen forces shaping their paths. Some researchers hypothesize that a massive, distant planet, often referred to as Planet 9, could be shepherding these bodies into similar orbital alignments, explaining their clustered orbits and unusual trajectories. These extreme objects are not just curiosities, they offer profound insights into the history and structure of the solar system. Their presence suggests that the Sun's gravity extends far beyond the Kuiper Belt and scattered disk, reaching distances hundreds or even thousands of AU from the Sun. They may also provide evidence of the Sun's early environment. When the Sun formed, it likely existed in a dense cluster of stars. Close stellar encounters could have perturbed objects into highly elongated orbits, scattering some outward into the regions we now recognize as the inner Oort Cloud. In this sense, Sedna and its kin are frozen records of both solar system formation and the Sun's earliest interactions with its stellar neighbors. Moreover, these oddball objects blur the boundary of what we traditionally consider the solar system. While the Kuiper Belt and scattered disk are still relatively well-defined, ETNOs occupy a more ambiguous zone, straddling the line between the solar system proper and the inner reaches of the Oort Cloud. Their extreme orbits are a warning that defining the solar system's edge is far from straightforward. It is not marked by planets or belts alone but by a complex hierarchy of distant objects, gradually giving way to interstellar space. The physical characteristics of these objects are also intriguing. Sedna, for instance, is about 1,000 kilometers in diameter and has a reddish hue, indicative of surface tholins, complex organic compounds formed through long-term radiation exposure. These surfaces are likely ancient and unaltered, providing a pristine glimpse into the composition of material from the outermost solar system. Studying these oddballs can therefore reveal both the chemical and dynamical history of the Sun's gravitational domain, as well as the processes that operated in the outer reaches of the protoplanetary disk. While only a handful of ETNOs have been discovered so far, astronomers believe that there could be hundreds or even thousands more awaiting detection. Many of these objects are so faint and distant that current telescopes struggle to spot them. Upcoming instruments, like the Vera C. Rubin Observatory, are expected to revolutionize our understanding of this population, potentially uncovering a vast halo of objects that stretches the known solar system to distances approaching the inner Oort cloud. In summary, Sedna and other extreme trans-Neptunian objects are cosmic trailblazers, silently orbiting in the farthest reaches of the Sun's gravitational influence. They are reminders that the solar system is not a neat, confined space, but a vast, multi-layered structure extending far beyond the planets, Pluto, the Kuiper Belt, and even the scattered disk. They hint at gravitational forces in distant regions that are still largely unexplored, and they serve as a bridge to the hypothesized inner Oort cloud, where icy bodies extend thousands of AU from the Sun. These oddballs compel us to reconsider what it means to define the edge of the solar system. Rather than a single boundary or line, the solar system is a gradation of influence, stretching from the inner planets out through belts, disks, and isolated extreme objects, finally reaching a region where the Sun's gravity is faint and the interstellar medium dominates. Sedna and its kin mark the threshold of this transition, preparing the way for the concept of the Oort cloud. Beyond the extreme trans-Neptunian objects like Sedna, we enter a truly vast and largely hypothetical region, the inner Oort cloud. While we have direct observations of Kuiper Belt and scattered disk objects, the Oort cloud remains mostly inferred, predicted through mathematical models, and hinted at by the origins of long-period comets. This inner Oort cloud represents a transitional zone between the distant scattered disk and the outermost reaches of the solar system's gravitational domain. It is a region that stretches thousands, even tens of thousands, of astronomical units from the Sun, distances so vast that our human imagination struggles to grasp them. The concept of the Oort cloud was first proposed by Dutch astronomer Jan Oort in 1950, based on the observation of long-period comets entering the inner solar system from seemingly random directions. These comets did not appear to originate from the Kuiper Belt or any known planetary region. Oort hypothesized that a massive, spherical cloud of icy bodies surrounded the Sun at distances of roughly 2,000 to 20,000 Australian dollars, forming a reservoir for these comets. The inner Oort cloud, sometimes called a Hills cloud, is the portion closer to the Sun, occupying the region from about 2,000 Australian dollars to perhaps 20,000 or 50,000 Australian dollars. Its presence bridges the gap between the extreme objects like Sedna and the vast outer Oort cloud, which may extend nearly a light-year away. The inner Oort cloud is believed to be composed primarily of icy planetesimals, remnants from the formation of the solar system that were scattered outward by the giant planets, particularly Jupiter and Neptune, early in the Sun's history. These objects are thought to be largely undisturbed, preserving ancient material from the solar nebula, including water, methane, ammonia, and other volatiles. Unlike the Kuiper Belt or scattered disk, the inner Oort cloud is spherically distributed, not confined to the plane of the solar system. This spherical geometry arises because the gravitational perturbations from passing stars, the tidal effects of the Milky Way, and interactions with the giant planets over billions of years have randomized the orbits of these distant icy bodies. Because of its extreme distance, the inner Oort cloud is extremely cold. Objects there experience minimal solar radiation, and their surface temperatures are likely near absolute zero, making them frozen, inert relics of the solar system's youth. This makes direct observation nearly impossible with current telescopes. No spacecraft has yet reached this region, and even the most distant probes like Voyager 1 and 2 are only beginning to touch the outskirts of the heliosphere at around 120 Australian dollars. The inner Oort cloud, at thousands of AU, lies far beyond our reach, which is why its existence is inferred rather than directly observed. Despite this, the inner Oort cloud has important consequences for understanding the solar system. It serves as the likely source of many long-period comets, which can have orbital periods of thousands to millions of years. Occasionally, gravitational nudges from passing stars or galactic tides perturb an inner Oort cloud object, sending it on a trajectory toward the Sun. These comets provide crucial insights into the composition and dynamics of the distant solar system, acting as messengers from a region we cannot yet explore directly. The inner Oort cloud also reveals the vastness of the Sun's gravitational influence. While the Kuiper Belt and scattered disk are relatively close in astronomical terms, the inner Oort cloud stretches to distances that dwarf the entire planetary system. To put this in perspective, the outermost planets orbit within 30 to 50 AU, while Sedna and other ETNOs reach a few hundred AU. The inner Oort cloud begins where these extreme objects end, starting at roughly 2,000 Australian dollars, a distance over 50 times farther than Sedna's aphelion. In effect, the inner Oort cloud is a vast halo of material surrounding the Sun, forming a gravitational bridge between the known solar system and the interstellar medium. Studying the inner Oort cloud, even indirectly, also helps us understand the solar system's early history. Models suggest that during the Sun's formation in a stellar nursery, interactions with nearby stars could have contributed to the distribution of objects in the inner Oort cloud. Some icy bodies may have even been captured from other stars in the Sun's birth cluster. In this sense, the inner Oort cloud is not just a repository of solar system remnants, it is a record of the Sun's interactions with its galactic neighborhood at the very beginning of its life. The inner Oort cloud is also critical in defining the boundary between the solar system and interstellar space. While the heliopause marks the limit of the Sun's energetic influence, the inner Oort cloud marks the farthest reaches of its gravitational dominance over small bodies. Even at thousands of AU, the Sun's gravity can control the orbits of these icy planetesimals, shaping their trajectories over millions of years. It is a quiet, distant frontier, far beyond the planetary realm, yet still undeniably part of the Sun's domain. In summary, the inner Oort cloud is a vast, spherical shell of icy objects that extends thousands of times farther than Earth's orbit. It bridges the gap between the distant, eccentric trans-Neptunian objects and the outermost reaches of the solar system, serving as a source for long-period comets and a record of the Sun's formative interactions with its stellar environment. Though it remains largely invisible to us, it reminds us that the solar system is not confined to the planets or even the Kuiper Belt. Instead, it stretches outward across an immense, largely unexplored expanse, gradually fading into the galactic ocean. Beyond the inner Oort cloud lies the even more remote and enigmatic outer Oort cloud, a hypothetical realm so vast that it may stretch up to a full light-year, or roughly 63,000 astronomical units, from the Sun. If the inner Oort cloud is a vast spherical halo of icy remnants and minor bodies, the outer Oort cloud is the solar system's ultimate frontier, occupying the boundary where the Sun's gravitational dominance wanes and interstellar forces begin to govern the motion of objects. While no direct observations of these objects exist, their existence is inferred from the behavior of long-period comets and dynamical models of the solar system. The outer Oort cloud represents the extreme edge of the Sun's gravitational influence. It is hypothesized to contain billions, perhaps trillions, of icy bodies, most of them small, cold, and dark. These objects are remnants of the early solar system, displaced outward by gravitational interactions with the giant planets or perturbed by passing stars during the Sun's early years in a stellar cluster. Over billions of years, these icy planetesimals settled into loosely bound, highly elliptical orbits that form a spherical distribution around the Sun. Unlike the inner Oort cloud, which remains somewhat bound and less influenced by external forces, the outer Oort cloud exists in a tenuous balance. Its members are still technically bound to the Sun, but a slight disturbance from a passing star, a molecular cloud, or even galactic tidal forces could eject them into interstellar space. One of the key reasons scientists hypothesize the outer Oort cloud is the existence of long-period comets, those with orbital periods of thousands or even millions of years. Observations show that many of these comets arrive from seemingly random directions, not confined to the plane of the solar system. Their trajectories suggest a roughly spherical source region, consistent with a distant Oort cloud rather than the more flattened Kuiper Belt or scattered disk. When a comet from the outer Oort cloud is nudged by a gravitational perturbation, it begins a journey inward, sometimes bringing it as close as the inner planets. In this way, the outer Oort cloud acts as a vast repository of icy bodies and a conveyor belt for some of the solar system's most spectacular visitors. The distances involved in the outer Oort cloud are staggering. While Neptune orbits at $30 and Pluto at roughly $40, the outer Oort cloud could extend 1,000 times farther than Pluto's orbit, or more. At such distances, the Sun's gravity is exceedingly weak. Objects in this region move slowly, taking millions of years to complete a single orbit. They exist in a nearly inertial state, coasting in deep darkness, only occasionally nudged inward by external forces. These objects are effectively the last bastions of the Sun's influence before the vast expanse of interstellar space takes over. The outer Oort cloud is also highly sensitive to galactic forces. Stars passing within a few light-years of the Sun can subtly alter the orbits of these distant bodies, sending some inward as comets and ejecting others entirely. The tidal forces of the Milky Way galaxy itself, gradual stretching and compressing effects caused by the galaxy's gravitational field, can also perturb Oort cloud objects. These interactions explain why the outer Oort cloud is more diffuse and loosely bound than the inner Oort cloud. It is a fragile, tenuous structure at the boundary of the Sun's gravitational domain. Though hypothetical, the outer Oort cloud has profound implications for our understanding of the solar system. Its existence suggests that the Sun's influence stretches far beyond the planets, the Kuiper Belt, the scattered disk, and even the inner Oort cloud. It represents the final stage in the hierarchical structure of the solar system, a vast envelope of icy relics encasing the entire planetary system in a diffuse, spherical shell. In a very real sense, it defines the outermost limit of what can be considered the Sun's domain, marking the transition from the solar system to the vast, largely empty space between stars. Studying the outer Oort cloud also offers insights into the early history of the Sun and the solar system. The outermost icy bodies may have been influenced by nearby stars during the Sun's formation in a dense stellar nursery, and their current distribution reflects billions of years of galactic interactions. In effect, the outer Oort cloud preserves a fossil record of both the solar system's formation and its journey through the Milky Way. Despite its extreme distance, the outer Oort cloud is crucial for understanding interstellar connections. Objects ejected from this region become free-floating interstellar bodies, like the recently observed Oumuamua and comet Borisov, offering the first glimpses of material from beyond our solar system. In this way, the outer Oort cloud is a bridge between our Sun's domain and the vast expanse of the galaxy, hinting at the exchange of material between stars. In summary, the outer Oort cloud is the solar system's ultimate frontier, a hypothetical, vast, spherical shell of icy objects extending up to a light-year from the Sun. It is the final gravitational domain of our star, home to billions of primordial remnants, and the source of long-period comets that occasionally visit the inner solar system. Though we cannot observe it directly, it defines the outermost limits of the Sun's influence, connecting our planetary neighborhood to the vast interstellar medium beyond. If the outer Oort cloud is the distant, hypothetical frontier of the solar system, comets are the messengers that confirm its existence. Long-period comets, those with orbital periods ranging from thousands to millions of years, serve as the only direct evidence we have for the inner and outer Oort cloud. Though astronomers have never directly observed these distant icy bodies, the paths and behaviors of comets provide a compelling indirect window into the solar system's most remote regions. Long-period comets are distinguished from their short-period cousins by their orbital characteristics. Short-period comets, like Halley's Comet, typically originate from the Kuiper Belt or the scattered disk, with orbital periods of less than 200 years and orbits confined largely to the plane of the solar system. Long-period comets, by contrast, arrive from all directions, their orbits highly inclined and often nearly parabolic or hyperbolic. This spherical, isotropic distribution suggests a source that envelops the Sun in all directions, a characteristic perfectly consistent with the hypothesized Oort cloud. When a long-period comet is observed entering the inner solar system, its trajectory can be traced backward. Analysis of its orbit shows that these comets originate from vast distances, thousands or tens of thousands of AU away. The orbits are typically extremely elongated, bringing the comet from a near-stationary existence at the outer fringes of the Sun's gravity all the way into the inner planetary system, often for the very first time in its lifetime. This journey transforms a distant, frozen relic into a blazing spectacle visible from Earth. The mechanism by which these comets are perturbed into the inner solar system is fascinating. Even though the Sun's gravity dominates nearby space, small gravitational nudges from passing stars or the tidal forces of the Milky Way galaxy can disturb the orbits of Oort cloud objects. Over millions of years, these perturbations occasionally shift an object's orbit inward, sending it on a long plunge toward the Sun. When such a comet approaches the inner solar system, the Sun's warmth causes its icy surface to sublimate, producing the iconic glowing coma and tail. In this way, long-period comets are not just spectacular celestial events, they are physical evidence of the otherwise invisible Oort cloud. The diversity of observed long-period comets also supports the idea of a vast, spherical Oort cloud. These comets come from all directions, without preference for the plane of the planets. Their random inclinations and varied orbital orientations suggest a source region that is isotropic, enveloping the Sun rather than confined to a disk. This matches the expected structure of the inner and outer Oort cloud, a spherical halo of icy bodies scattered across tens of thousands of AU. Some comets show orbital characteristics that suggest they were influenced by the outer Oort cloud, while others likely originated closer in the inner Oort cloud. For example, a comet with an aphelion of 50,000 Australian dollars might be considered an outer Oort cloud object, while one perturbed from a few thousand AU could be from the inner Oort cloud. The presence of both populations of comets demonstrates that the Oort cloud is not a monolithic shell but a multi-layered reservoir, gradually fading into interstellar space. In addition to providing evidence of the Oort cloud structure, comets also reveal its composition. The ices that sublimate to form the coma and tail contain water, methane, ammonia, carbon dioxide, and organic compounds. These materials are thought to be pristine, largely unchanged since the early solar system. By studying the composition of long-period comets, scientists gain insight into the primordial materials that formed not only the planets but also the vast outer reservoirs of icy objects. Each comet becomes a chemical time capsule, linking us directly to the Sun's distant, frozen frontier. Even though we have never directly observed the Oort cloud, the statistical distribution of comets further supports its existence. Calculations suggest that billions of icy bodies must occupy these distant regions to account for the frequency of long-period comets observed in the inner solar system. The large numbers are necessary because only a tiny fraction of Oort cloud objects are nudged inward over a given time frame. In essence, each long-period comet is a rare messenger from a massive, unseen population that spans the Sun's outermost domain. The Oort cloud's relationship with comets also highlights the dynamic nature of the solar system's edge. While planets and even the Kuiper Belt follow predictable orbits, the outer reaches are more chaotic. Long-period comets illustrate this beautifully, showing how distant gravitational forces, galactic tides, and stellar encounters can gently tug objects inward, transforming inert icy bodies into spectacular phenomena that traverse millions of kilometers. In this way, comets serve as proof that the solar system extends far beyond the planets, Pluto, the Kuiper Belt, and the scattered disk. They are not merely transient visitors, they are ambassadors from the Sun's distant gravitational domain, carrying information about the size, structure, and composition of regions we cannot yet explore directly. Without comets, our understanding of the inner and outer Oort cloud would remain purely theoretical, lacking the tangible evidence that brings this distant frontier into the realm of scientific study. Ultimately, comets demonstrate that the solar system is layered and immense. From the planets to the Kuiper Belt, the scattered disk, extreme trans-Neptunian objects, and the inner and outer Oort cloud, comets trace a path through these successive boundaries, linking us directly to the Sun's farthest reaches. They remind us that defining the edge of the solar system is not a matter of simply locating the last planet or the outermost dwarf planet. It is about tracing the Sun's gravitational and energetic influence across immense distances, far beyond what is immediately visible. Beyond the outer Oort cloud and the comets it supplies lies another way to conceptualize the solar system's edge, not through icy objects or energetic particles, but through the very force that binds the system together, gravity. The Sun's gravitational influence extends far beyond the planets, the Kuiper Belt, and even the distant Oort cloud, gradually waning as it encounters the gravitational pull of other stars and the galactic environment. This region is described by a concept known as the Sun's heliosphere, or gravitational sphere of influence, which provides a useful, if somewhat abstract, measure of the solar system's ultimate boundary. The heliosphere defines the volume around a celestial body in which it dominates the gravitational attraction of orbiting objects, relative to the influence of a more massive body nearby. In the case of the Sun, the heliosphere represents the region where its gravity holds sway over small bodies, planets, asteroids, icy objects, despite the gravitational tug of neighboring stars in the Milky Way. Beyond this limit, stellar encounters and galactic tidal forces can easily perturb objects, sending them into interstellar space or altering their trajectories in ways the Sun alone cannot control. Calculating the Sun's heliosphere involves considering the Sun's mass, the mass of nearby stars, and the Sun's distance from the galactic center. Estimates suggest that the Sun's heliosphere extends roughly 1 to 2 light-years, which is about 63,000 to 126,000 astronomical units. This is enormous compared to the orbit of Neptune at $30 Australian, Pluto at roughly $40 Australian, and even Sedna at nearly 1,000 Australian dollars. In other words, the Sun's gravitational influence stretches orders of magnitude beyond the familiar planetary system, encompassing both the inner and outer Oort cloud and potentially defining the farthest reaches of the solar system in a gravitational sense. The Sun's heliosphere helps clarify why some objects remain bound to the solar system while others do not. Objects within this sphere, even if extremely distant like those in the Oort cloud, are still technically under the Sun's gravitational control. Objects slightly outside this sphere, however, are more easily stripped away by the gravitational influence of nearby stars. For instance, passing stars, molecular clouds, or even the combined tidal forces of the Milky Way can perturb outer Oort cloud objects, sending them into interstellar space or nudging them inward as long-period comets. The heliosphere, therefore, provides a theoretical limit on the Sun's ability to retain objects over astronomical timescales. Importantly, the heliosphere is not a hard, fixed boundary. It fluctuates over time depending on the Sun's position in the galaxy and the proximity of other stars. During the Sun's early history, when it likely formed within a dense star cluster, the effective heliosphere would have been much smaller because nearby stellar neighbors exerted significant gravitational influence. Today, in the relatively empty space of the galactic disk, the Sun's heliosphere is larger, allowing it to maintain a tenuous grip on the outer Oort cloud. In this sense, the heliosphere is both a dynamic and context-dependent concept, reflecting the interplay between local and galactic gravitational forces. The heliosphere also provides context for interstellar interactions. When a rogue star passes within a few light-years, the outer regions of the Oort cloud may feel its influence more strongly than the Sun's. Such encounters can strip away icy bodies, inject them into the inner solar system as comets, or even exchange material between star systems. Thus, the heliosphere defines not just a limit of influence but a transition zone where the solar system's autonomy begins to give way to the broader galaxy. From a practical perspective, the heliosphere helps astronomers define the solar system in a way that is physically meaningful. While the heliopause marks the boundary of the Sun's energetic influence, and the Oort cloud delineates the outer limits of observable icy bodies, the heliosphere describes the outermost region where the Sun's gravity is dominant. Objects within this sphere are still ours, bound by the Sun, whereas beyond it, gravitational forces from the galaxy and other stars become increasingly important. It's important to note that the heliosphere is vastly larger than the heliopause or even the Oort cloud. While Voyager 1 crossed the heliopause at about 121 Australian dollars, and even the outer Oort cloud may extend to roughly 100,000 Australian dollars, the Sun's heliosphere stretches beyond these distances, encompassing a region where the Sun's pull is stronger than that of any nearby star. This illustrates that the solar system is not just a planetary arrangement but a hierarchical, gravitationally structured system, with multiple layers of influence extending across unimaginable distances. In a broader sense, the Sun's heliosphere underscores the interconnectedness of the solar system and the galaxy. While we often think of the solar system as isolated, its outermost regions exist in a delicate gravitational balance, influenced by nearby stars and galactic tides. Understanding the heliosphere helps us appreciate this balance and highlights that the solar system does not have a singular, fixed edge. Instead, it gradually transitions from the familiar planetary orbits to distant icy bodies and ultimately to a vast, tenuous gravitational boundary where the Sun's control wanes. In summary, the Sun's heliosphere represents the region where the Sun's gravity dominates over the combined influence of nearby stars, offering a conceptual edge of the solar system in a gravitational sense. Stretching roughly 1 to 2 light-years, it encompasses the planets, Kuiper Belt, scattered disk, and the inner and outer Oort cloud. While not a physical barrier, it defines the farthest reaches of the Sun's influence, marking a transition from solar dominance to galactic forces. It is the final gravitational frontier, reminding us that the solar system is immense, multilayered, and intricately connected to the broader Milky Way. Crossing the boundary of the heliosphere, as Voyager 1 and Voyager 2 did, was a monumental milestone in space exploration, but it is important to understand that this does not mean a spacecraft, or any object, is now freely traveling through what astronomers define as interstellar space in its broadest sense. There is a subtle but crucial difference between leaving the heliosphere and entering the interstellar medium, and understanding it helps clarify the structure of the solar system and the environment beyond. The heliosphere, as we've discussed, is a vast bubble inflated by the solar wind, the continuous outflow of charged particles and magnetic fields from the Sun. It extends well beyond the planets and even past the distant Kuiper Belt, scattered disk, and extreme trans-Neptunian objects, eventually giving way to the heliopause. Crossing the heliopause, as Voyager 1 did in 2012, signifies that a spacecraft has left the region dominated by the Sun's solar wind and magnetic field, entering a zone where the properties of space are largely shaped by forces beyond the Sun. At this point, the local plasma environment changes dramatically, the flow of solar particles diminishes sharply, and cosmic rays increase substantially. This was the signature event that confirmed humanity had touched the boundary of the Sun's energetic influence. However, the space just beyond the heliopause is still not truly interstellar space in the sense of being free of solar gravitational influence. The Sun's gravity continues to dominate the orbits of distant icy bodies in the inner and outer Oort Cloud, keeping them loosely bound in enormous, tenuous orbits that can stretch thousands to tens of thousands of astronomical units. Even though Voyager is outside the bubble of solar wind, the spacecraft is still well within the Sun's heliosphere, the region where the Sun's gravitational pull remains stronger than that of nearby stars. In other words, crossing the heliopause is an energetic boundary, not a gravitational one. Interstellar medium, by contrast, refers to the space between stars in the galaxy, where matter is not dominated by a single star but is instead shaped by the collective forces of many stars, galactic tides, cosmic rays, and magnetic fields. It is a vast, diffuse environment composed of neutral hydrogen, helium, ionized gas, dust grains, cosmic rays, and pervasive magnetic fields. Its density is extremely low, far less than even the emptiest regions of the heliosphere, but it defines the medium through which stars travel and through which the solar system itself moves. When we speak of truly venturing into the interstellar medium, we are referring to moving beyond the point where the Sun's magnetic and particle influence is negligible and where the local galactic environment governs the properties of space. The distinction is important because leaving the heliosphere is a sudden, measurable event, while fully traversing the interstellar medium is a gradual process. As Voyager continues its outward journey, it is still under the gravitational influence of the Sun and will remain so for tens of thousands of years, slowly moving through a medium shaped not only by the Sun's gravity but also by the distant presence of other stars and the overall galactic field. Over immense timescales, as objects drift farther from the Sun, they may eventually become interstellar wanderers, free of the Sun's gravitational pull, truly immersed in the galactic environment. Comets that are perturbed from the outer Oort cloud and ejected from the solar system are examples of bodies that will eventually become interstellar objects, joining the vast population of material traveling through the galaxy. Understanding this distinction also informs our perception of the solar system structure. The heliopause marks the end of the Sun's particle-dominated influence. The Oort cloud represents the outer boundary of gravitational control, and beyond that lies the interstellar medium, the galactic environment in which stars and their planetary systems drift. The transition is not abrupt but occurs across immense distances. For example, Voyager 1 crossed the heliopause at about $121, yet it remains deep within the Sun's heliosphere, millions of times closer to the Sun than the nearest star. The heliosphere acts like a protective bubble, while the interstellar medium is the vast, shared galactic environment, influencing all stars equally. This distinction also highlights the layered and hierarchical nature of the solar system's edges. Leaving the heliosphere is a crossing of a boundary defined by energy and particle flow. Venturing into the interstellar medium is a crossing defined by dominance, where no single star dictates the dynamics of the local environment. The solar system, therefore, does not have a single edge but a series of gradually receding boundaries, from planets to belts, clouds, and gravitational spheres, each layer defining a different type of influence: magnetic, gravitational, or dynamic. In practical terms, this is why we must be precise in our language. Voyager 1 and 2 are often celebrated as having entered interstellar space, but technically, they entered interstellar space in the sense of leaving the heliosphere. They are still within the Sun's gravitational domain, still moving through a region influenced by the Sun's mass, yet immersed in plasma, cosmic rays, and magnetic fields shaped primarily by the wider galaxy. Truly being in the interstellar medium in the pure sense would mean moving well beyond the Oort cloud and out of the heliosphere, a journey that would take millions of years at Voyager's current speed. Thus, The distinction between leaving the heliosphere and traversing the interstellar medium is both scientific and conceptual. Leaving the heliosphere marks the Sun's loss of energetic dominance, while moving through the interstellar medium represents the transition to a space where the galaxy's collective forces govern the environment. This layered perspective underscores the immense scale of our solar system and the vast distances separating the Sun's immediate influence from the broader galactic environment. The solar system does not exist in isolation. It is embedded within the grand structure of the Milky Way galaxy, moving through a dynamic environment filled with interstellar gas, dust, and magnetic fields. Understanding the solar system's galactic neighborhood provides critical context for everything we've explored so far, from the planets and Kuiper Belt to the distant Oort Cloud and the transition into interstellar space. The Sun, like all stars, is not stationary. It orbits the center of the galaxy at an average speed of approximately 828,000 km per hour, completing a full orbit roughly every 225 to 250 million years. This orbital journey carries the solar system through regions of varying density, temperature, and composition, subtly influencing the outer reaches of our solar system over cosmic timescales. Our solar system resides in the Orion Arm, a minor spiral arm of the Milky Way situated between the larger Sagittarius and Perseus arms. This relatively quiet neighborhood allows the Sun to travel without frequent, close encounters with massive stars or dense molecular clouds, which could gravitationally disturb the outer Oort Cloud. Nonetheless, the Sun periodically passes through regions of higher interstellar density, known as interstellar clouds, which are composed of gas and dust. These clouds are not obstacles in the traditional sense. They are diffuse, but they exert subtle gravitational and pressure effects on the heliosphere and the distant boundaries of the solar system. For instance, passing through a denser region of interstellar gas could compress the heliosphere, altering its size and shape, while also perturbing the orbits of loosely bound Oort Cloud objects. The motion of the solar system through the galaxy is not perfectly circular. The Sun oscillates slightly up and down relative to the galactic plane, like a bobbing object in a vast galactic ocean. These vertical oscillations expose the solar system to regions of differing interstellar density, potentially increasing the rate of cometary influx from the Oort Cloud during periods of higher density. Galactic tides, the subtle stretching effects caused by the Milky Way's overall mass distribution, also act on distant solar system objects, nudging Oort Cloud bodies and sometimes sending them inward as long-period comets. These forces, though incredibly weak compared to the Sun's gravitational pull in the inner solar system, accumulate over millions of years and help shape the distribution of material in the farthest reaches of our stellar neighborhood. The interstellar medium in our region of the galaxy is not uniform. It contains variations in density, temperature, and composition. The local bubble, for example, is a region of unusually low density, hot gas thought to have been carved out by ancient supernova explosions. Our solar system currently moves through this bubble, which influences the heliosphere's size and the flux of cosmic rays reaching the inner solar system. In denser regions, such as molecular clouds rich in hydrogen and dust, the heliosphere could shrink, allowing more interstellar material to penetrate deeper into the solar system. These interactions are subtle but ongoing, illustrating that even the most distant solar system structures, like the Oort Cloud, are not entirely isolated from the galaxy. The solar system's trajectory also defines the timescale of potential encounters with other stars. On average, the Sun passes within 1 light-year of another star only once every several 100,000 years. Even these distant encounters can slightly perturb outer Oort Cloud objects, occasionally sending them toward the inner solar system as long-period comets. More dramatic, though rare, stellar flybys could strip material entirely from the Sun's outer reaches, populating interstellar space with objects that were once bound to our star. Over billions of years, these interactions subtly shape the structure and population of the solar system's outermost boundaries. The galactic environment also influences cosmic radiation. As the Sun orbits the Milky Way, it moves through regions with varying densities of cosmic rays, which originate from supernovae and other energetic galactic phenomena. These high-energy particles can penetrate the heliosphere and interact with planetary atmospheres, icy bodies, and even comets traveling inward from the Oort Cloud. Changes in cosmic ray intensity, modulated by both solar activity and the solar system's motion through the galaxy, help us understand the interplay between local solar influences and the broader galactic context. Thus, our solar system is both vast and dynamic, situated in a living galaxy rather than a static void. From the planets orbiting within a few dozen AU to the outer Oort Cloud stretching tens of thousands of AU away, everything is embedded in a moving galactic environment. The Sun's orbit through the Milky Way, its passage through interstellar clouds, and the subtle forces of galactic tides all influence the structure and evolution of the solar system's outermost regions. Far from being a fixed, isolated bubble, the solar system is a dynamic entity interacting with the galaxy at every scale. Understanding our place in the galactic neighborhood emphasizes that defining the edge of the solar system is not just about the heliopause or the outer Oort Cloud. It also requires considering the solar system as part of a larger galactic ecosystem. The Sun's motion, nearby stars, interstellar gas, and cosmic rays all shape the environment in which planets, comets, and distant icy bodies exist. This perspective transforms our understanding from a simple planetary system to a layered, dynamic structure embedded in the Milky Way, continually influenced by forces far beyond our immediate solar domain. As remarkable as the Voyager spacecraft are, having journeyed beyond the heliopause and into the Sun's distant realm, they are limited by their speed, instrumentation, and the sheer distances involved. They will take tens of thousands of years to traverse even a fraction of the Oort Cloud, making direct exploration of the outer solar system beyond the heliosphere effectively impossible with current technology. Recognizing these limitations, scientists have been designing concepts for new missions specifically aimed at exploring the outer boundaries of the solar system and venturing deeper into interstellar space. Among the most ambitious of these is the proposed Interstellar Probe. The Interstellar Probe concept is designed to surpass Voyager in every significant way: speed, instrumentation, and scientific capability. Its primary goal is to travel much farther than any previous spacecraft, potentially reaching distances up to 1,000 astronomical units or more within a human lifetime. By doing so, it would provide unprecedented insight into the outer heliosphere, the heliopause, and the interstellar medium beyond. Unlike Voyager, which carries instruments designed primarily for planetary encounters and limited deep space studies, the Interstellar Probe would carry advanced sensors to measure plasma, magnetic fields, cosmic rays, interstellar dust, and neutral gas, giving scientists a comprehensive picture of the space between stars. One of the key objectives of the Interstellar Probe is to study the structure and dynamics of the heliosphere in 3 dimensions, something that Voyager cannot do on its own. While Voyager 1 and 2 provide point measurements along their trajectories, a dedicated probe with a carefully planned path could map the shape and size of the heliosphere as it interacts with the interstellar medium. This would help answer lingering questions about the solar wind's interaction with interstellar gas, the nature of the helio sheath, and the processes that govern cosmic ray modulation at the boundary. Understanding these interactions is crucial not only for astrophysics but also for preparing for future deep space exploration by humans or robotic spacecraft. Beyond the heliosphere, the Interstellar Probe could make the first in situ observations of the interstellar medium at distances well beyond the Oort Cloud. Measurements of interstellar gas density, composition, magnetic fields, and cosmic ray fluxes could confirm models developed from indirect observations and simulations. These data would provide insight into the galactic environment through which the Sun travels and how it has influenced the formation, evolution, and current structure of the solar system's outermost regions. Studying interstellar space up close would also help astronomers better understand the life cycle of matter in the galaxy, including how comets, dust, and gas move between star systems. Another fascinating aspect of such a mission would be its potential to detect and study distant objects in the inner and outer Oort Cloud. Although the probe would likely pass at distances too large for direct imaging of individual icy bodies, instruments could measure their gravitational effects, dust trails, or even detect distant cometary activity. This would provide empirical evidence for regions that remain largely hypothetical, bridging the gap between theory and observation. In essence, the Interstellar Probe could confirm the presence and structure of the Oort Cloud, providing direct measurements where previously we relied solely on the indirect evidence provided by comets. To achieve the necessary speeds for these distant reaches, mission planners are considering advanced propulsion methods, such as solar sail technology, high-energy chemical propulsion, or even gravity-assist maneuvers from Jupiter and potentially other planets. These techniques would enable the spacecraft to reach hundreds of astronomical units within a few decades rather than centuries, making the exploration of the solar system's farthest boundaries a feasible endeavor within a single generation. This acceleration is crucial. Without it, even modern spacecraft like Voyager would take tens of thousands of years to reach the outer Oort Cloud. The Interstellar Probe would also continue humanity's legacy of gathering long-term data from the solar system. Voyager has provided over 4 decades of continuous observations of space, magnetic fields, and cosmic rays, and a dedicated interstellar mission could extend this dataset by orders of magnitude, providing detailed time-resolved measurements of the changing solar environment as the Sun moves through the galaxy. Such information could help scientists understand not just the outer solar system today, but also how it evolves over millions of years, shaped by the Sun's motion and galactic interactions. Proposed missions like the Interstellar Probe also carry profound philosophical and scientific significance. They represent humanity's desire to push beyond familiar boundaries and explore the unknown reaches of the Sun's influence. They would take us past the heliopause, through the Oort Cloud, and into interstellar space, giving us our first direct encounter with the medium that exists between stars. Such missions will transform our understanding of where the solar system ends, how it interacts with the galaxy, and how our star's domain fits into the broader cosmos. Ultimately, future interstellar missions will allow us to answer questions that have remained purely theoretical for decades. How large is the Sun's heliosphere? What is the precise structure and composition of the inner and outer Oort Cloud? How does the interstellar medium affect the evolution of the solar system's most distant objects? And how do these regions interact with the galaxy at large? Unlike the Voyagers, which are enduring symbols of human curiosity and technological ingenuity, new probes will carry the potential for unprecedented discovery, directly exploring the vast, largely invisible frontier that extends far beyond Pluto, Sedna, and the heliopause. In summary, proposed missions like the Interstellar Probe represent the next generation of solar system exploration. They are designed to surpass Voyager in speed and scope, reaching hundreds or even thousands of astronomical units, providing direct measurements of the heliosphere, the Oort Cloud, and the interstellar medium. These missions will transform our understanding of the solar system's boundaries, offering unprecedented insight into the transition from solar influence to the galaxy's dominion, and paving the way for humanity's first detailed exploration of interstellar space. As we reach the culmination of our exploration, it becomes clear that defining the edge of the solar system is not just a matter of measuring distances or cataloging celestial bodies. It is a journey into the very nature of boundaries, influence, and human curiosity. From the familiar planets to the distant icy fringes of the Oort Cloud, and beyond to the interstellar medium where the Sun's dominance wanes, the solar system reveals itself not as a fixed, tidy structure, but as a layered, dynamic, and evolving environment. Each step outward, from the inner planets to the Kuiper Belt, the scattered disk, extreme trans-Neptunian objects, and finally to the outer Oort Cloud, has expanded our understanding of what it means to belong to a solar system. The progress humanity has made in exploring these realms is staggering. In just over half a century, we have sent robotic emissaries like Voyager 1 and 2 to the outermost boundaries of the heliosphere, measured the solar wind and magnetic fields, detected cosmic rays, and confirmed the transition into the local interstellar medium. These missions have provided the first empirical proof that the Sun's influence, though immense, is finite, and that beyond it lies a vast, largely unexplored region shaped by the galaxy itself. The very fact that we can even conceptualize these distant realms, from Sedna's lonely orbit to the hypothetical outer Oort Cloud hundreds of thousands of AU away, is a testament to human ingenuity, scientific modeling, and our relentless curiosity. Yet, for all our progress, the solar system's outermost reaches remain shrouded in mystery. The inner and outer Oort Cloud, the domain of long-period comets and icy remnants, have never been directly observed. Extreme trans-Neptunian objects hint at unseen influences, possibly a hidden massive planet or the gravitational whispers of distant stars, leaving us to infer their presence from subtle orbital patterns. Even the Sun's heliosphere, though theoretically defined, is a conceptual boundary rather than a physical one, reminding us that the edge of the solar system is not a single line but a gradient of influence, gradually transitioning into the vast, diffuse interstellar medium. Each discovery opens new questions. How many bodies lie hidden in the outer Oort Cloud? What secrets do they hold about the early solar system? How does the Sun interact with the galaxy on timescales spanning millions of years? This tension between what we know and what we have yet to discover is where the wonder truly lies. The solar system, once imagined as a collection of planets orbiting a solitary star, now emerges as a vast, hierarchical structure, embedded in a living galaxy. Its boundaries are defined by energy, gravity, and motion, shaped by interactions both local and cosmic. The journey from the Sun's surface to the edge of the heliosphere is not merely spatial. It is a journey through layers of physics, history, and celestial dynamics, revealing the interconnectedness of planetary, stellar, and galactic systems. Looking forward, the promise of future missions like the Interstellar Probe brings both anticipation and humility. Even as Voyager continues its decades-long trek into the heliosheath and beyond, new spacecraft could provide the first direct observations of regions that until now have been inferred through models and comets' indirect messages. We are on the threshold of a new era, one in which humanity may, for the first time, fully traverse the Sun's gravitational domain, measure the interstellar medium in situ, and explore the mysterious frontier of the Oort Cloud. These missions will push the boundaries of our technology, our endurance, and our imagination, and will redefine the solar system once again, not merely as a collection of planets, moons, and asteroids, but as an immense, layered system in dynamic interplay with the galaxy. Ultimately, reflecting on the edge of the solar system reminds us of both our accomplishments and our limitations. We have mapped the inner and outer planets, discovered distant dwarf planets and icy belts, sent robotic explorers into interstellar space, and developed theoretical frameworks to understand the Oort Cloud and the heliosphere. Yet beyond the edge, beyond the reach of our probes and even our telescopes, lies a vast frontier of mystery. Billions of icy bodies, interstellar gas, and gravitational influences we have yet to touch. The solar system is at once familiar and unfathomable, a testament to human curiosity and the vastness of the universe we inhabit. This duality, our ability to explore and yet our continued ignorance, is what gives the solar system's edge its profound significance. It is both a mirror of human progress and a reminder of the unknown. It challenges us to keep reaching outward, to extend our understanding, and to embrace the vast, layered, and interconnected cosmos in which our Sun and its family of objects exist. Standing at this threshold, we see not just the limits of the solar system, but also the limitless potential for discovery that lies beyond, waiting for the next generation of explorers and the next wave of scientific insight. In the end, defining the edge of the solar system is an invitation to look farther, think deeper, and marvel at the scale, complexity, and beauty of our cosmic home. From the first planets observed through early telescopes to the icy fringes of the Oort Cloud and the interstellar medium, the journey outward is both scientific and philosophical, blending rigorous measurement with awe and wonder. Each new layer we uncover, each comet we trace, and each probe we send is a reminder that the universe is far larger and more intricate than we can fully grasp, but that through curiosity, perseverance, and exploration, we can continue to push the boundaries of our knowledge ever outward. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.